Okay, so last time I've shown you that for a particle, okay, so moving in a central force field, okay, so the equation for its trajectory or the equation for its orbit in general is given by this equation over here, right? And then I also told you that with this equation, okay, so which is expressed in polar coordinates, okay, so it's actually corresponding to the equation of the so-called conic section, right? And if I convert, right, so if I convert this equation in polar coordinate into Cartesian coordinates, and this is the form that I would get, okay? And if you just take this general form, okay, so and if you plug in different value for this epsilon, which I call this eccentricity, okay, so you'll be able to show that it will give all these different shapes, okay, so corresponding to these different values of the epsilon. Okay. So here let me just quickly show you how it is the case. Okay, so for the epsilon greater than 1, right? So what do we have to consider? So epsilon greater than 1, I'm sorry, not greater than 1, greater than yes, greater than 1, epsilon equals 1, and then epsilon is between 1 and 0, right? So and then finally epsilon is 0. Right? So if you go ahead and plug in this epsilon greater than 1, right? So into this equation over here, so what you see is that the first term over here, right? So let me just write it one more time. Okay, so for epsilon greater than 1, right? So this equation becomes basically, I'm just copying everything. Okay, in this term, right? So if it is greater than 1, okay, so then this 1 minus epsilon square would be smaller than 0 actually, but it doesn't matter. So it is, this one is still just a constant, right? And then for the denominator, right? So you can see that if I have this epsilon greater than 1, then this 1 minus epsilon square also is smaller than 0, right? So but it doesn't matter because I have a square outside, right? So this one is still a positive constant, right? So but then if I write the second terms, okay, so y squared divided by alpha squared divided by 1 minus epsilon squared, right? So this 1 minus epsilon squared, as I said, is smaller than 0. So let me just instead write it as epsilon squared minus 1, right? So that this whole thing is greater than 0. Okay, so but then I add a minus sign in front, right? So you can see that this form, right? So this term minus this term equals a constant, right? So that's exactly looks like a hyperbola. Okay. So now if I have this epsilon equals 1, so what happened? Epsilon equals 1, so you need to be careful here because you don't want to just use this final result here because this 1 minus 1. Okay, so instead I'll just go back to a few steps earlier where I have this equation over here, right? So this equation, right? So this equation is derived from this equation, right? So if I have this epsilon equals 1, then I have this 1 minus epsilon squared to be 0. Right, so what do I have is this y squared plus 2 alpha x minus alpha squared equals 0. Right. and this is clearly a parabola, right? So, but it's not open upward, right? So, but open on the side, right? So it's not y equals x squared, that type, right? But instead, it's y squared equals x, right? So plus something. So this is a parabola. And then for this one, right? So I don't need to repeat it. So just look at this equation by itself. Now, all the terms here are positive, right? So it's this terms plus the other term, right? So x squared divided by something plus y squared divided by something. That gives me a constant, and that would be, of course, it's an ellipse. Okay. Finally, if I have this epsilon equals 0, okay. So what you see is that this, if I just plug in epsilon equals 0 to this equation, right? So what you see is just x squared divided by alpha squared plus y squared divided by alpha squared equals 1. Right. So that's a circle, right? So of radius alpha. Okay. So, and actually, I want to focus on the case of ellipse a little bit in a minute. Okay. So, but here, right? So now mathematically, right? So we know that different eccentricity values give us different shape. Okay. So, but also remember that the eccentricity is related to the physical parameters by this relation over here, right? So which I have shown you last time, right? So but I didn't talk about it at that point, right? So but here let's look at it, right? So epsilon greater than 1. So what is the requirement for that, right? So if you want epsilon greater than 1, right? So that means that it must be 1 plus some positive number, right? So what are the parameters in this? So E is the total energy, right? So L is the angular momentum, M is the mass, and what is K, right? So K is the, just remind you, right? So force is given by minus K divided by R squared. Okay, so that's the K. And for gravitational case, then you understand that K is actually my G and M. Okay, but just to make the symbol easy, so I just put this as K. Okay. But anyway, so in that case, so I want this whole term to be greater than 0, right? So all the other terms must be positive with this L squared, K squared, and so forth. So that the only thing that may be positive or negative is this E, right? So that is to say, if you want a hyperbola orbit, you are required to have this total energy of the particle greater than 0. Okay. So then for epsilon exactly equals 1, then that means I want this whole term to be 0. So that means E is 0. So similarly, you can show the requirement for the energy for the ellipse and circle, right? So within these two different conditions. So, and the first two, which are the hyperbola and parabola, okay, we call them open orbit, right? So you can see from this picture again, right? So this is the hyperbola and this is the parabola, right? So and you can imagine that if your particle is moving with these two orbits, so that means the particle can go away indefinitely, right? So until it reach infinity, right? And that makes sense, right? Because you could imagine that because the total energy of the particle is greater than 0, well, or equals to 0. So what does that mean, right? So remember that the total energy is given by, of course, it's Ke plus Pe, right? So it's 1/2 mv squared minus what is PE is K divided by R, right? So if E is greater than 0 or equal to 0, right? So what it really means is that if you consider the case where R tends to infinity, right? So what happened is that the minus K over R, the potential energy terms will tend to 0, right? So at infinity, you only have the kinetic energy term, right? And in this case, right, so since your total energy is greater than or equal to 0, so that means that at infinity, the particle either has some finite energy, kinetic energy, or no energy, right? So, but in either case, those are physically acceptable, right? So, however, right, so if you go down to the two other cases below, right, so where you have this E to be negative, right, so then you understand that the part is impossible for the particle to get to infinity, right? Because if that is possible, then that means that the kinetic energy will have to be negative, right? So that's not physical, right? So whenever you have this energy smaller than 0, then the orbit, so those are the closed orbit. Okay, so the particle always has some finite distance. Okay, so from the source of the force. Okay. So these two statements, okay, so just repeat what I just said. Okay. So that's one thing to remind you is that, so when I write down this four criteria in this table, right, so it gives you an impression is that, right, the hyperbola has the highest energy, right? So the parabola has the second highest, and then ellipse lower, and then the circle the lowest. Okay. So indeed, if we follow these four exactly these four orbits in this picture, right? So that's indeed the case, right? Highest energy and then up down to the lowest energy. Okay. However, I should remind you that circular orbit, okay, does not necessarily have lower energy than an elliptical orbit. Okay, and I will show you later in an example. Okay, so when do we have the case that the circular orbit have a greater energy than the elliptical orbit? But you might ask that then but then will that violate these relations? Okay, so but the thing to notice is that when you see these inequality or equality, you can see that these numbers, well, it's not really a constant, right? So mk square and 2 are constants, but L square itself is actually not a constant, right? So because L is the angular momentum, right? So you could have cases where you change E and also change L simultaneously. And of course, you can also have cases where you can change E, but with L fixed, right? So that really depends on the situation. Okay, I'll come back to this later. Okay, so but as I said, I want to spend a bit more time just specifically on the case of elliptical orbit. Okay, so this is the important case. Okay, so because, well, circle, of course, is very simple, don't have much to talk about, right? So you understand that when we talk about this orbit of planets, okay, so most of the time we will be talking about elliptical orbit. Okay. So just a reminder, okay, so maybe you are familiar with this already, is about the basic geometric properties of an ellipse. Okay, so in particular, okay, so I want to emphasize the quantity of the eccentricity, right? So because I talk about the 4 cases, right? So they are all depending on this eccentricity. So this is the ellipse equation that I have, right? So the eccentricity, okay, so is given by the square root of 1 minus d squared divided by a squared. So from this picture, right, so you can see this A is the semi-major axis, this D is the semi-minor axis, right? And now, right, so the eccentricity, what does it tell you? It really tells you, right, so it gets from the ratio between the B and A. Okay. So B and A, right, so this divided by this, right, so that tells us how compressed the circle is, right? So you can imagine that if you imagine that the ellipse is formed by a circle, and then you just compress it on one of the dimension, right? So, and if you compress it more, right? So if you compress it, and it will become something like this, right? So how much it gets compressed, right? So can be quantified by this length divided by this length, right? So that is the B divided by A. So if it is not compressed at all, right? So then this B divided by A is just exactly 1. Then your eccentricity is just 0, right? So that is the larger the eccentricity is, right? So you could imagine that you get a more compressed or elongated shape, okay, for the ellipse. Okay, so that's what happened. Okay, and also an ellipse. So there are 2 points that I indicate over here. Okay, so they are called the foci of the ellipse. Okay, so and what are the geometrical significance of these 2 points over here? Okay, and actually, there's one way to construct the ellipse is the following, right? So is that you have this paper, okay, so and then you nail down these 2 points. So these 2 points are the foci that I just talked about. Okay, so and then you kind of tie a string, okay, so to these 2 points and also a pencil. Okay, so the string is a loop, right? So and it forms a triangle like this. Okay, so what happens is that if you just set this up and then you just try to move your pencil, right? So and then if you just draw it and then complete one cycle, then you realize that this is how you draw an ellipse, right? And for a circle, for circle, it's more simple. But for circle, you just use 1 point at the center, right? And then you tie a string and then you draw it, and that's the circle. Right? So you have these 2 foci, right? So displaced from each other by some distance, then you draw an ellipse, right? So and that if I actually do that, so mathematically, what does that mean? So that means that if I'm going to right, so I have this point and this point, and then I have the 2 string, right? So as I said, like this. Okay. So then this point, I'll just call that x, y. Okay. And the coordinate, the position of these 2 foci are actually given by, so actually I labeled here already. So here is a epsilon 0. Okay, so and this is minus a epsilon 0. Okay. And right, so because the length, okay, so the total length of this triangle is fixed, right? So that means this distance, okay, plus this distance has to be a constant. Okay, so no matter I'm here or I'm here, right? So that means, right, so the distance, right, so this distance plus this distance, that is this one, right? Equals to some constant. So what is that constant? Okay, so that constant is actually, if you just consider the case where you drag your string such that you are right over here, right? So if you drag it to this point, right, the green one, then you realize that this length plus this small length is exactly equals to the entire major axis, right? So the entire major axis is, that would be, of course, is 2a. Okay. So I think I won't really finish the whole derivation, but then actually you can try to show it by yourself, right? So but let me just maybe do 1 or 2 steps. Is that if you go to just keep this on the left hand side, and then if you just move this term to the right hand side, okay, and then do square, okay, so for both sides, so what you have is the following. Okay, then if you try to move all the terms except the square root term to the left hand side, and then you just further square both sides again and simplify, okay, you will be able to show that x squared divided by a squared plus y squared divided by b squared is indeed equals 1. Given that, right, so the eccentricity is given by this over here. You'll be able to show that. Okay. So that's how an ellipse can be constructed, right? So knowing the given the two locations of the foci. Okay. So now in polar coordinates, okay, in polar coordinates, we are taking this form over here. And now with this alpha and epsilon, right, so you can relate that with this a and b, okay, just with these two equation over here. The last time I also mentioned that in this case, okay, so although this is also an ellipse, right, so but I've already shown you that this is actually not centered at origin, right? So that is right. So because if I convert this equation, right, so to the Cartesian coordinates, right, so it's this one, right? So this is not an ellipse that center at 0, 0, right? So instead, it is an ellipse center at this point. And this point actually exactly is at one of the foci, right over here. So therefore, if I have, let's say I have a polar coordinate system, okay, using this point as the origin, okay. So then this equation will represent an ellipse that looks like this. Okay. Centered over here. Okay. So with this, I want to show you a few pictures that I draw using computer. Okay, so you can see that. So this is the same equation I have, right? So if I just fix this alpha value, okay, so if I change the eccentricity, okay, so you can see that. Okay, so for this blue one is the case where I have this epsilon to be 0. So this is a circle, right, centered at this origin. Okay, so and then I have some finite epsilon, right? So 0.4. You can see that is this one over here, and then 0.8, this one, and then 0.6 and 0.8. Okay. So you can see that the aspect ratio, right? So it's getting looks more and more like an ellipse, right? So, but not just that, you can see that it's not centered over here, right? So this is the common one of the common foci of all the shapes that I'm drawing over here. Okay. And on the other hand, right? So if I just fix the epsilon, okay. So but if I change this value of alpha, okay. So what you can see is that you are getting bigger and bigger ellipse. Okay. So but the aspect ratios, okay, so are all actually the same. Just the overall shape getting bigger and bigger. Okay, so now let's relate this again, this alpha and this epsilon with the real physical parameter. Okay. So you can see that well, this is I have this particle m, right, moving around in an elliptical orbit, and this is the source of the force, right? So just like a planet and the star. Okay. So from this equation, right, so you can see that. So if I just again, let me just write in this form instead, right? So this R is alpha plus, right? So the minimum possible value of R, right, so occurs when you have the greatest denominator, right, which is the when this cosine theta is 1, right? So that's why the smallest possible distance is, which I call this R mean. Okay, so it's this alpha divided by 1 plus epsilon. Okay. From this picture, right, so it's easy to see that it's right over here. On the other hand, right, so the largest possible distance happens when you have this smallest denominator. That is theta equals pi. Then I have this point over here. Okay, so let's see. And now, if I have this particle, if I give you the velocity, or no, I should say that if I give you the total energy, well, if I give you the total energy of this particle, right, and you know that this is moving around this orbit, right? So that means that you know R, right? So then you should be able to find out the kinetic energy of this particle, right? So at all different points, just by using conservation of energy. Okay. So this is just a small exercise for yourself, right? So you give you a given E, right? So you should be able to find out the kinetic energy at this R min and this R max. Okay. So if you want to find out the magnitude of the velocity, right? So just if I just set here, right? So that should be easy, just conservation energy, right? So if you actually want to find out the V vector, okay, so you should be there's more a bit more work to do actually. So because right, so if I just look at this picture again, right? So you know that at any given point, right? So the velocity vector, right? So should be tangential to your trajectory, right? So like this. And you can see that I'm drawing a bigger arrow here because you know that at this point, right, because of the closest distance, you have the greatest velocity. Right? So and as you move away, right, so the velocity, the magnitude of the velocity, right, should be decreasing, and then get to a minimum over here. So, but at any different particular point, right? So the velocity actually has two components, right? So one is this right over here, right? This is the radial direction, right? So let me just call this VR r hat. So and then the other, right? So as you are familiar with now, is the transverse direction, right? So which I call this V theta theta hat. So and you know that this VR, right? So is your R dot, right? So and this V theta is your R theta dot. Okay. So if you want to find, right? So this velocity R dot and this R theta dot, right? So first of all, right? So the R dot can be found by using conservation of energy. Okay, so this is the formula that I've shown you early on in this chapter. Right? So this is KE plus PE equals E. And next, if you want to find out the R theta dot, right? So again, you can make use of this conservation of angular momentum. So you should be able to find out this R dot and R theta dot. So and another problem over here is that there are actually 2 points, 2 special points where we have this one of the component of the velocity to be 0, right? So that is this component of the velocity to be 0. Okay, so at these 2 points. So actually, in the picture, it's really easy to see why at this point and this point the velocity are 0, right? So because at this point, if I'm going to draw the R vector, the R direction and theta direction, you know that is something like this, right? So this the R direction is this, right? And this point, right? So the R direction is this, right? So exactly at these 2 edges, this R vector is clearly, right? So perpendicular to your velocity vector, this green arrow, right? And that's why the R dot, right? So there's no radial direction of velocity, right? So at these 2 points, right? So that's why you have this R dot to be 0, right? So that's easy to see from the graph, but if I want to show it using equation, right? So what do I need to do? Right? So all I need to do is that if R dot is 0, so that means that this whole thing has to be 0. Right? And this whole thing here, so let me just write it out over here, is 2 divided by m, right? So u of r, right? So I just have this minus k divided by r. So that's why minus u is plus k divided by r, minus L squared divided by m squared r squared equals 0. And well, with just a little bit of rearrangement, right? So you can see that this can be written as a quadratic equation for 1 over r. Okay. Right. Using 1 over r as the variable, right? This one is a quadratic equation. And if you just use the quadratic formula, you will find that this 1 over r equals 1 plus or minus this. Okay. And I hope this one and this one look familiar to you, right? So because this term over here is exactly the eccentricity epsilon. And this one is the alpha. Right, so that is when r equals alpha divided by 1 plus or minus epsilon, then I have this r dot equals 0. Right, so that's exactly our r mean and r max. So here, let's go back to look at one of the things that we learned early in the chapter, is so-called the aerial velocity. So remember that for the area velocity, right? So what it really means is that I have this position vector, right? So at a particular time, right? So this is the r at t, right? So sometime later, this is r t plus dt. And the area swept out by this position vector r is given by this small, this narrow triangle over here, right? So, and this is what I call the dA, right? And this dA divided by dt, right? So because of the conservation of angular momentum, I show you in the last lecture, right? So this is given by L divided by 2m over here. So I'm going to make use of this to actually find the period of the orbit. So what is the period? The period is the time taken for this particle to complete one full cycle. Okay, so that's the period. Okay. So now, in principle, right? So how do you find the period? Well, in principle, of course, you can use make use of this v equals ds dt, right? So that's in principle, you can, if you integrate both sides, so this s is equals to integral of this. Actually, I just need the magnitude. Right. So this s, what I'm saying is the total length, right, of the circumference of this ellipse. That's the s. So if you integrate the speed, right, so over time, right, so it go from 0 to 1 period, right, so then that's how you get to s, right? So s is the, you know what it is, right? If it is given, and velocity, right? So you can calculate that, right? So then from this relation, right, so you may be able to find out the period t. So however, right, so here, as I said, I'm not going to do it this way, right? So I'm going to make use of the aerial velocity. Okay. So what you could imagine is that if this particle keep going, right? So then this R vector eventually will sweep out the entire ellipse, right? So that is the whole entire area of the ellipse itself. Right? So that's why, right? So if I just integrate both sides, so what I mean is that, right? So if I integrate both sides, like this, right? So integral from 0 to 1 period. So the right-hand side is actually very easy because L divided by 2m is a constant, right? So the right-hand side is just L divided by 2m times t, right? And then the left-hand side, right, as I said, it is exactly the area of the ellipse itself. Okay. So that is, right? So if I just do the integral, so this is what I get. So, and remember how this A and B can be related to this alpha and epsilon, as I showed you earlier. And this alpha and epsilon are related to the physical parameters and which are given here and here. So then the period, right? So from this relation here, period can be written like this, and then further expressed as this equation over here. Right? And now, if I square both sides, okay, I'll be able to say that t squared is equals to all these parameters times a cubed, right? So this is known as the Kepler's third law. So you might have, again, you might have learned about this before, but maybe you have only seen the proof for the special case for a circle, right? So but here, right, so it's that in general for an ellipse, right, so you can have this relation over here. So here, I'll just lay out the three Kepler's law, right? So again, as I said, you might have heard of them, but you might have not seen the mathematical derivation formally, right? So, and I just tell you one more time, right? So is that the planets move in elliptical orbit about the sun, okay, with the sun at one focus. Okay, so so notice that Kepler, right? So at that time, right? So he summarized, right? So his observational data, right? So to get to these three laws. Right? So but now we understand that all from Newtonian mechanics, right? With the inverse square force law. Right? And the second one, right? So the area per unit time, right? Sweep out by a radius factor from the sun to a planet is constant, right? So that's what we said is due to the conservation of angular momentum, right? And then the third one is what we just showed, right? So and notice that, right? So these well, at least for the second one, right? So or the at least for the second one and the third one, right? So you could imagine that even you don't have this 1 over r square, right? So you just need to have this conservation of angular momentum, then you also be able to do that. Oh, but for the elliptical orbit, right? So but one thing to notice is that if you don't have 1 over r square, then you don't have the elliptical orbit. Okay, so here we'll take a break. Okay, so we'll take a break. I thought someone is trying to do promotion. Okay, so then I'll leave the time to CUHK Co-op. Right, so they would like to introduce their program. Okay, so here is an exercise problem that I would like you to spend a few minutes to think about. Okay, so what this says is that I have a particle over here initially, so with some initial velocity v naught. Okay, so and it is at a distance r naught away from the source of the central force. Okay, so and you can see that the initial velocity v naught. Okay, so it's actually perpendicular to the position vector r over here. So the question asked that finding the range, okay, or the value of this initial velocity v naught, okay, such that the orbit, okay, so is in one of the following shape. So over the discussions so far, right? So I have been just basically using the total energy and the total angular momentum, right? So to characterize the particle, right? So here, okay, this is the situation where you may be more familiar with, right? So is that I give you some initial position and some initial velocity, and then I ask you to study the behavior of this particle. Okay. So of course you could imagine that what you need to do is just to convert the information that I just gave you, right? So into energy and angular momentum. So, okay, so of course the formula we need to use, right, is the total energy, right? So the total energy would be, right, so this KE plus PE, right? So this is the quantity we want to look at first, right? And also, oh, okay, so this is E, and the other one is the angular momentum. So angular momentum, so I give you the initial distance and the initial velocity, right? So the angular momentum would be just m times r naught times v naught. So for A, right? So we know that we need E greater than 0, right? So and then the second one is E equals 0. So actually, it's all written over there. Okay. So now, right? So if you just take this equation, right? So if you just go to set it greater to be 0, right? So what you will be able to find is that V0 has to be greater than square root of 2k divided by MR0. So similarly, right? So if you just set this equals 0, then the V0 is just equals this square root. Okay. And now let's talk about the ellipse and circle. Okay. So of course, right? So for the ellipse, right? So I know that this is smaller than 0 this time, right? So first of all, right? So I would require this V0 to be smaller than this one. However, well, this is not the end of the story, because remember that it's smaller than 0, and it also have to be greater than this quantity, right? So minus mk squared divided by 2l squared. So, and if I just, right, so write down this part of the inequality, right? So if I just write down this part of the inequality, right? So what I have is the following. Okay, so it's 1/2 mv0 squared minus k divided by r0. So greater than this, right? And this one, right? So this L square, remember, is also depending on this R0 and V0, right? So this quantity here, I'll just write it as like this. So here I'm looking for a requirement, a constraint, a requirement for the V0, right? So then let me write this thing, right? So using V0 as the variable. Okay, so in fact, okay, it can be shown that this equation can be written like this. So what I'm doing is that I'm actually multiplying both sides by V0 squared, and you'll see a quadratic equation. Okay. So this is a quadratic equation in V0 squared. Okay. Not just V0, but V0 squared. It's more convenient to write it this way, as you'll see, because again, I have this nice quadratic equation, and this is, in fact, can be written as V0 squared minus k divided by MR0 square all squared. So V0 has to satisfy, okay, so this inequality here, right, in addition to this one that I have already written down. So what is the requirement then? You can see that, right, so this is a square outside, right? So that means as long as I have this whole thing to be non-zero, then I can satisfy this equation here. So that is as long as this V0 is not equals to k divided by m r naught, then we are fine. So then let me put it over here. Okay, so finally, I have to consider the circle. Right? So for the circle, right? So this inequality, right, just becomes equality. Right? So that is for the circle, V naught has to be exactly equals to this. Okay. So these are the all 4 cases, and it actually correspond to this picture one more time. Okay, so you can see that in all these 4 cases, 4 orbits, right? So we have the same distance over here. Right? So I call this R naught and this V naught. Right? So then depending on the V naught that you pick, right? So you will end up at different orbits, right? So in this picture. So if I'm going to just draw a line, right? So to summarize the result, or something like this. So let me draw a line for the V naught. So this is the 2k divided by m r naught. Right. So if I'm exactly having this value of V naught, then this would be parabola. Right. And if V naught is higher than that, right? So all this, then it would be hyperbola. Okay. And the other value I want to draw over here is this k divided by m r naught, which is this one. So exactly at this value, then we get a circle. And if you're somewhere between here, then you get ellipse. So then there's one more thing, okay, missing. Okay, in this line. Okay, what about here? Okay, what about here? Even below this value. So if I look at the results I just got, right? So again, once again, if I look at this one, I require V naught to be smaller than this value, right? So that is over here. And also, I require this one to be not equal to this value. So that is, in fact, from my mathematical result, all I'm saying is that all over this range, okay, I should get the ellipse, right, except at this point. However, in this picture, right, so it doesn't really show what happened if we have the velocity even smaller than this value. Right? Because you could imagine that if you are somewhere between here right? So you are getting the ellipse, which are all kind of bigger than the circle, right? So like if you may get an ellipse like this black one, but you might also get an ellipse like this one. Right? If you get a velocity greater than the black one, right? And you might also get an ellipse like this one. Okay, drawing is not good, but you understand the idea. Okay. But all these ellipses, right? So are kind of bigger. They're all bigger than this circle, right? So when your velocity is within this range over here. So then it's reasonable to say that, right? So if you are having a value smaller than this, then you have ellipse, but somehow that ellipse has to be smaller, even smaller than this circle, right? So, and what happened is the following. Okay, so you will get, in fact, you'll get an ellipse that looks like this. So, but what is the significant difference between this purple ellipse and all the ellipses that are outside? Is that let me again label the point of the focus. Right? So this is the source of the force, remember. So in all the previous cases, right? So this point and this point is the so-called the R mean, right? So remember we have this R mean and R max, right? So this distance over here, right? Remember it's the R mean, the minimum distance, okay, between this point and your particle. Right? However, once you get an ellipse that is actually smaller than this circle, like this purple one, right? From the picture, you see that, right? So this line over here for the purple circle is no longer the R mean, actually. Right? You can see that. Right? This one is, of course, not the nearest distance. Instead, this one becomes the nearest distance. So that is for the purple case. Right? So that distance over here is actually our max. That's what happened. Right? So that is to say, if you get this velocity to be even lower than this value, so it's not impossible to draw an ellipse that take this distance to be the R mean. Instead, it has to be the R max. So then this will show you a situation where, right, so the elliptical orbit can actually have a lower energy, okay, so than the circular orbit. Right? So I told you earlier in the lecture, right, so to remind you that there are some situations where the circular orbit actually has higher energy of the elliptical orbit. And this is the situation. Okay. Okay, so let's do one more example for here. Is that, so suppose I have a particle, okay, so originally is doing a circular motion, okay, so around the source, right, so given by this. And now, suddenly, if this constant k, okay, it decreases to half its original value. So this is not a very physical situation, but just imagine that this k, right, at a particular time, it suddenly becomes k divided by 2. So that means the force suddenly becomes weaker. So, and you could imagine that if that happens, then you will not be able to sustain this circular orbit. Right? The orbit will have to change the shape. And here we want to show that the orbit will become a parabola. So that is, it is moving at some time, suppose it's here. So once the force becomes weaker suddenly, right, so you can imagine that the trajectory may be looking something like this. And this, I want to show that this is a parabola. So, and what is the requirement for parabola? Okay, parabola means that the kinetic energy plus potential energy, right, so has to be 0, right? So E, the total E has to be 0. That's what we are trying to show. Show capital E is 0. So before anything happens, so before the K is changed, right? So I have this total energy, which I call E naught. And this is given by 1/2 mv squared minus K divided by R. Let me just say that the initial radius is this capital R. So, and if I give you some V, right, so, and what is the value of R? Right? So it cannot be arbitrary, right? So because to sustain, actually you can either just make use of this result, right? So make use of this result over here. So you tell me that this V has to be equals to the square root of K divided by mr, or you can go back and make use of something that you have learned before, right? So when you learn about this circular motion, right? So you remember that this centripetal force mv squared divided by r has to be equals to this attractive force minus k divided by r squared. So from here, right, so you can also obtain the value of v, right? And in fact, here I don't care so much about the v itself. I want mv squared, right? So that, let me just put it here, right? So that means mv squared is this minus k divided by r. Right? So 1/2 mv squared is minus k divided by 2r. Right, so that is initially, right, so my energy is this minus k, oh, not minus, right? So here I just consider the magnitude, right? So there's no minus. So it's k divided by 2r minus k divided by r. So this is what we have initially. So as the k is changed, but suddenly the force is half, right? So what happened is that at that instant, right? So the velocity won't be affected immediately, okay, at that point. So that is the ke. So as you change the force, right, at least at that instance, right, so ke remains the same, okay. But the pe has changed from k divided by r divided by minus k divided by 2 divided by r. So that is to say, right, so this term over here, it suddenly becomes K divided by 2R. So then the E would be K divided by 2R minus K divided by 2R. Then that becomes 0. Right? And that's why the trajectory will become a parabola. Okay. So the next thing I want to talk about, okay, is to introduce a new term, okay, which is called the so-called the centrifugal term. Okay. So we are just basically looking at the same problem over here, right? So but using a slightly different way to look at it. So at this point, right, so you're very familiar with this expression for the total energy, right? So I have already eliminated the theta dot, okay, by using this conservation of angular momentum. Okay. So now if I just look at this energy term itself, right, and if I don't tell you that I'm actually working on the central force particle orbiting problem, right? So if you just look at it, you may also tell me that this is actually describing a system that is just having one coordinate variable, right? Because all you see is the R and R dot. Right? So that is, let's try to think of this really as a one-dimensional problem, right? That only has R. Okay. The particle moving along R. So in that case, right, so what you will see is that the first term, right, the first term is the kinetic energy. And everything after that, okay, so these two, you can treat the whole thing as a potential energy. Right, so you know that actually that's not the case if we are actually talking about the central force problem, right? So both of these terms are kinetic energy, right? So and only the third term, potential energy. However, as I said, if you really look at this whole thing, and I don't tell you that I'm considering this two-dimensional central force problem, right? You can tell me that, yeah, this is just a one-dimensional motion with this first term to be the kinetic energy and the second and the third term to be the potential energy. So now that is written here, right? So the second and the third term are the potential energy. And in fact, okay, so we call it the so-called the effective potential, okay, the effective potential energy. Okay. So, and of course, you know that this is not real, right? So because this term is really a kinetic term, so that's why we call it a fictitious potential, right? And we combine the real potential, the U of R, right, and the kinetic energy term that is associated with the angular momentum. Right? So, and in fact, this term over here is called the centrifugal potential. Okay. So because and it gives rise to a fictitious force that is known as the centrifugal force. Okay. So I think you have heard of this term when you learn about the circular motion. Okay. Not a real force, but a fictitious force, or sometimes we call it the pseudo force. But effectively, right? So this centrifugal force, right? So tends to repel the particle away from the origin, right? So because this potential, right, is not with a minus sign, right? So this potential, right, U of R is minus something, so this is attractive. But here you can see that this is all positive, so that's why it gives effectively it gives a repulsive force. Okay. So if I just go to draw a picture, it's more clear to see what happens, right? So here, right, so I have this dashed line over here, right, is just the minus K divided by R, the real potential, right? And then this one, right, is the so-called, as I just said, right, the centrifugal potential, right? So this is the positive term over here, right? So the entire effective potential, right, is that you add this curve, right, so to the other curve over here. Then, in fact, the shape that you get for the effective potential is this solid line over here. So you can see that if you really consider this black solid line, so the force is not always attractive, and it's also not always repulsive, right? Because you can imagine that if you are if your particle is here, right? So then you experience an attractive force, right? So that the particle tends to go to the position with the lower potential energy. On the other hand, if you're right over here, right, so the particle will tend to go this way, but getting repelled. So you can see that because there's a minimum point over here. And in fact, right, so this minimum point, right, so give you this minimum possible value of this U effective, which is this value over here, right? So this is easy to find, right? So you just need to take derivatives and find the minimum value. That's nothing more than that. So now, using this picture, okay, let's consider all the 4 different kind of orbits again. Okay. So again, the hyperbola, parabola, ellipse, and circle. Okay. So what do we have over here? So if you have this energy, okay, so to be greater than 0, okay, so that means you're up here. Right? So suppose my total energy, right, so is given by this red dashed line. Okay. So and that means your particle is allowed to move. Where is it allowed to move? Right. So it's allowed to move whenever you get a positive or 0 kinetic energy. Right. So that is this particle is not allowed to move closer than this purple line over here, right? So because if your energy is that much, right? So if you go to this side, then you will get this negative kinetic energy, right? Because in this region over here, right? So the total energy is higher than your potential energy, so then you cannot. The potential energy is higher than the total energy, then you cannot get the positive kinetic energy. So you are not allowed to move over here, but you are allowed to move anywhere in this region. So similarly, if I have this parabola, so that is my energy is at 0, right? So then this time you are allowed to move, right? So anywhere. The minimum distance is over here. Let me correct the last one. Last one should be like here. Okay. So now, if I have ellipse, right? So my energy is at this blue level over here. Right? So then your particle, right? So will be allowed to move between 2 points. Okay, that is this point and this point. Right. Particle and free to move like this. So, and this really corresponding to what we had for the ellipse, right? So because for the ellipse, you indeed have the R mean and the R max, right? So this is the R mean, and this is the R max. So finally, right? So if your energy is exactly at the minimum value, right? So of the potential curve, then if you treat it as a one-dimensional problem, then you will say that the particle really cannot move anywhere but stay here. Right? But if you translate it back to our real 2D problem, okay, you understand that it corresponding to a circular orbit, right? Because for the circular orbit, the R is a constant, and the effective potential, right? So as I found for you, right? So the minimum point is at indeed this one, and this value, right? So we have already shown that it is indeed the same as this energy requirement. So this is just using another way, right? So to intuitively look at what happens, okay, so for the different situations over here. So I have a couple more minutes, but I don't think I will start the part 2 at this point. Okay, so I think I'll just stop here for today. So next time we'll come back with the part 2 of this chapter.